So welcome back. As you know, we've been moving along here. We're well into chapter 10. My hope here is to finish chapter 10, and I think we will, and do as many example problems as humanly possible here. But as I mentioned many times before, and we'll say it again, this is just a big chapter. 9 and 10 are big chapters, followed by 2 short chapters. So don't fall behind, because these 4 chapters wrap up really quick, because we go right into 11, boom, right into 12, boom, and then you're going to be ready for a test, believe it or not, here. And so you'll have whatever chapters that is, 9, 10, 11, and 12. So if you bothered to look ahead into the schedule, you know we only have 4 weeks of instruction left and 1 more week of finals. So that's and counting this week. So that's where we are headed. Now, if you recall, and maybe I should put the little chart over here again, but this whole chapter, I think, is best learned if you always think about what did we do for our, excuse me, our translational motion, and what are we doing now with our rotational motion. And we were in the middle of a long discussion about, well, I guess we had kinetic energy, which we said was 1/2 mv squared, which then led to a rotational kinetic energy, which we now write as 1/2 I omega squared, where this I is the moment of inertia. And what we noticed is it was a bit more complicated than regular inertia, because it was a sum of all the masses at the location. And so this is the part that we finished on Wednesday, saying, let's take a close look at this, because this, I think, is one of the harder concepts we do all semester. What is the idea of the moment of inertia, and how do you calculate it? And so you might recall we left off with this. We said, let's look at a rod. And so we took a rod, and we said, let's take this rod, and let's spin this rod about its center. And we said, what would the I of a rod about its center be? And I use this as an opportunity to go from a summation to an integral. And I think this is probably about the 4th time we've done it this semester. And I said, that's one of the important things I want to get across this semester is how do I take that step process. So what we did is we said, okay, let's look at this. And I divided the rod then into little chunks of mass and said, all right, if this is a little chunk of mass, and maybe this is another little chunk of mass, and you had all of those added together, what you are really saying is take the summation of mi/ri squared, but take the limit as each piece gets smaller and smaller and smaller. And so looking at that formula, we have an m and an r. One of those needs to go to 0 if you're going to change it into an integral, right? One of them needs to get smaller so we can have an infinite number of objects to add up. And so what we were left with is this integral of r squared dm. And then we proceeded to do the integral. But that's probably worth repeating over here. Maybe I'll even open it up into the chart just to make sure you remember that if you're not adding up discrete individual pieces, then what you have to do is add up or do an integral and sum up all the masses. Of course, if you recall in this, then our r squared would be x squared if you call this x equals to 0 as your origin. And so your mass is at the position x. The density is a little bit of mass in a little bit of space. And we ended up with this integral. And after we did a couple of steps, we got that 1/12 ml squared, where m, and maybe I should put a capital M here, so that you will not confuse then hopefully the whole mass of the rod with the mass of the individual pieces that we chopped it into. And of course we chopped it into an infinitely number of pieces, so each little mass is 0. So I don't think you'll have that confusion, but I do think this whole concept of going from a summation to an integral, you know, on your own, adding up masses instead of x's is completely new, you know, and not completely new in that the calculus is new, but new, and this is the first calculus-based class you probably have outside of your math class, your first applied math course. And so, you know, how do you do these things? What's the real meaning of the math? Using the math, you know, applied math is different than learning the math. So you may have done well in your calculus, but this still can be a challenging step, and so that's why I took some time to do this. Yeah.
In this case, what would L be?
Oh, and in this case, I should have pointed that out. L was the length of the rod. So we had then called the length of the rod L. So when we integrated these, we set our limits as starting way over here at the mass farthest to the left and adding up until we got to the mass farthest to the right, and that's what our integral came out to be.
So it's saying right there that the density is the change in mass with respect to length?
Yeah. So how much mass per length? And so we made that first substitution, and then in here we made a substitution where the density is also equal to the total mass over the total length. That's how we got rid of density. So we substituted density in for the advantage of converting a dm into a dx. Then later on, since we had density in the equation, we substituted density out and got total mass and total length. So we took advantage of the fact that it had the same density throughout, meaning that a little bit of mass over a little bit of length is the same as all the mass over all the length.
In this case, because it was all they were all the same mass on every place, that's why the density was kind of total mass over.
Right. So total mass over total length you might say would give you your average, but if it's a uniform, average means the same everywhere. So we got away with it this time. And most of your problems you will, but I think there's one in the homework there that doesn't have a uniform density, maybe even two. And so you have to actually then substitute in the density equation and do the integral for it. Well, like I said, I think this is one of the hardest steps, if not the hardest step of the semester. So it takes a while for this to sink in. This and torques. And the good news about that is you're introduced to here at 10, we revisit it in 11, and we revisit it in 12. And so hopefully by those 3 chapters it has sunk in that you're ready for the test on it. That's the idea. And the same with torque. We'll see it here in a few minutes, and we'll see it again in 11 and see it again in 12. So that kind of summarizes where we were, and let me just kind of keep going with this, because I could ask about different shapes. I mean, you wouldn't expect something of a different shape, such as this hoop. I'll move this out of the way. But if I grab a hoop, or if you want to call it a ring, something like this, or I guess I have another ring, it's kind of a different size, but still the same basic idea. What would be the moment of inertia of that shape of object? And would you expect it to be, you know, a 1/12 ml squared? Would you expect it to be the same as this rod? No. You'd expect that you'd have to go through it, right? And would you expect it to be the same as a disc? No. I would go through it, right? And so let's try that one. And so keep this one in the back of your mind, and don't forget it. But do remember, this is only valid for a rod. And also notice it's only valid about its center. When we were leaving on Wednesday, I gave you one final question. I said, do you think this would have came out to be the same if I was spinning it around some other point, say here, or its end point, I think is what I asked. No, you would expect to get a difference number. And you will. And so we'll talk about that in just a moment. But let's just spin things around its center for now. The centers are usually easier to calculate. And then I'll show you a little trick, fortunately. Off-center is actually pretty easy to calculate too. So we'll start with center, but even off-center is kind of nice here. So we'll start with the center. So let's try another one here. let's try what is the I for a ring. And again, let's say a ring about its center. All right, so again, imagine a ring, and then like I said, here's a good one to do. Here's my ring, okay? And if I kind of draw it in a two-dimensional picture here on the board and say, all right, well, what I know is this is supposed to be the sum of an MIRI squared. And we don't have individual discrete chunks, so we've got to chop them ourselves, and we've got to take the limit as those little chunks get smaller and smaller and smaller. And so if you kind of think about dividing this, and maybe I'll put it in blue again, but I can look at a little chunk of mass right there, or maybe another chunk there, or another chunk there, or another chunk there. But the point is, going through that same logic, you would quickly convert this into that integral. And so that is, like I said, a big, important step. That is taking math out of the math class and applying it. And like I said, that can be a tough step for people. Some people do it better than others. But applied math, like I said, really is what I call the grand thesis of our math. I mean, why do we care about the math? You know, how are we going to use it outside of our math class? And so that step is an important step. And watch as we do these integrals, I would say that half the integral, maybe even more than half the integral, is really done with the physics, looking at what is the meaning between each step. And so I'm back to, you know, what I started last week and I hadn't been doing since the beginning. It's don't just do the math, read the math. What does it mean? And this is a good example of that, because as we add it together here, and maybe I should put some labeling on here for the hoop, I'll call capital R the radius of the hoop. What would you say about, say, this R squared? What would this mean to you? Well, this capital R back here meant the radius of the individual chunks of mass. As you look at its geometric shape here, what is the R squared? Or maybe I should say, what is the little r squared? Isn't it the same as the big R squared? And so my first step is to say that little r is really now the same, at least in this case, as the big R. Now that wasn't the case over here. Over here, the little r was the same as the x, okay? Because that's what r meant, the distance the mass is from the rotational axis, which was x. But in this case, maybe I should have said the axis is kind of coming in and out of the board here, so it's spinning this way, and I should have emphasized that. It's spinning like a wheel. It's not spinning like this, okay? It's spinning like this, but as it spins around this axis right here, then all of this mass is the same radius away. So the little r becomes the capital R, and it becomes a constant, so I pull it out in front. And what's nice about that is I can even take the next step, very simple. What's this right here? Now that's just the total mass of the hoop, right? This is saying add up the sum of the individual mass. We don't even have to go through this process of saying, well, let's convert it to a density and let's convert it to a dx. Who cares about all that? Just stop back and read the math. This says you are adding up all the little chunks of mass. So if I take that chunk plus that chunk plus that chunk plus that chunk and I add up all those little chunks of mass, what am I going to get? Yeah, the total mass of the hoop. And so there's my answer for what is the moment of inertia of a ring about its center, right? Just add it up. Sure enough, there I have it. And so that one's, I think, even easier to do than this one. I've debated for years if I should do that one first versus that one. Maybe you guys can tell me. But I just like the linear nature of it. It makes the integral really easy to see. It throws in the density. And yeah. All right. And this one, although it's easier, it's kind of clever. You know, kind of not really doing the math, but looking at the physics of it. So let's go one more extension on this. Okay, so now that we've got two objects, we've got the rod, we've got the hoop. Could you do this one?
Can you rotate that about the other axis?
Oh, you mean this axis?
Yes.
Could we? Yes, we could, but I'm kind of hesitant because we never do this semester. Next semester we will. How's that? Yeah, yeah. All right. And so let's look at this one. And actually, maybe that'll be a fun one to do with you in lab. We'll rotate that one. But let's rotate this one around an axis through its center. How are you going to do that one? Maybe I'll just leave it up there so you can kind of look at it. And I suppose you might argue, other than this one has a hole in it, ignore that hole. Isn't it really kind of the same thing? Now, they don't really have the same thickness. And they certainly don't have the same radius. But keep that in mind that either of those shapes, which I call discs, really are going to come out to the same thing as this one, which almost is solid. I've got a couple of, I'll put it in your angle so it looks solid there. But this looks more like a cylinder than it does a disc. But whether it be a cylinder or whether it be a disc, as you see as we lay it out, we're going to come up with the same basic idea. And so how do you solve that one? So let's try that one. What is I for a cylinder? Or if you prefer to call it a disc, if it's kind of, when they're short cylinders, we like to call them discs. And if they're tall, narrow, then we call them cylinders. But as you'll see, the idea is pretty much the same. And I want to emphasize, you're going to be rotating it about its center. And I should even say symmetric axis here, because we're going to rotate it around, not, as you pointed out, not this way rotation, but this rotation, like a wheel. Okay, and so what is the moment of inertia of a cylinder or a disc about its center? Well, I'll tell you what. Why don't we do this? Where we think of the disc as a sum of a bunch of hoops. In other words, let's not go all the way back to the fundamentals here. I mean, we could go to here and add up all the pieces. But in doing that, wouldn't we go around a circle and get a hoop first? And then once we did that, wouldn't we add up all the hoops to get a disc? So I already did the hoop, so let me start there. I would say, all right, this then is the sum of the eye of a bunch of hoops, or maybe I should say rings here. And so let's add up a bunch of rings. The first ring plus the second ring plus the third ring. Now I say all that because in the problem we just did, we know the moment of inertia of a ring. It is the sum of capital M R squared. Now, just to make sure it's clear in your mind, I am going to put capital M and put the word ring underneath it. I am going to put capital R and put ring underneath it, because when I look at that M there, is it the whole M of the disc? No, that's not what I mean there. I mean the mass of the ring, the one I'm making. And do all the rings weigh the same amount? No, I wouldn't expect that either, because I would expect each ring having a different radius to have different amounts of mass. Okay, and so both of these are changing, of course. Each ring has a different mass, each ring has a different radius, sure. But could we solve this? How many rings do you want to chop it into? Right, so you got to take this thinner and thinner. What's the advantage of taking it thinner and thinner? What happens to the summation? Yeah, it becomes an integral, right? So what's going to 0? So yeah, let's look at one of these rings. I'll just pick one right here, draw it in blue. And as you start chopping that disk into 1,000,000, 100,000,000, 1,000,000,000, 1,000,000,000,000, quadrillion, what goes to zero? Is it the radius of the disk? Right? I mean, that's the radius of the disk, whatever here is. Now, you may be saying the thickness of the disk. Yeah, the thickness of the disk goes to zero. And the thickness of the disk would correspond to what number in here? The mass. So it's not the radius. So again, one of the tougher steps here may be paying close attention to what do we mean from our calculus. What goes to zero? Getting a good mental picture of the physics of went on. What does a summation mean? You know, what does an integral mean? Yeah.
I don't try to understand why you can't just say the thickness goes to zero.
Well, okay, I could say the thickness goes to zero, but what is that in this equation?
Well, it corresponds to the mass, but why can't you just use thickness?
Okay, but I guess because my next step is to say integral of d what? What do I put here? I have to put a variable that's in the equation, right?
Okay, so if you didn't want to use thickness, you'd have to replace.
Right, and I am eventually going to get to thickness. But I wouldn't want to do it at this step only because I need to say what is going to zero, you know, and what is a function that varies with the ring. Yeah. And I would agree then that just like we did back here, once we did that, the mass went to zero, but the mass became the thickness in the next step, because that's how I knew to do the limits of it was based upon space. So I had to change it to space. I had to change it to thickness. And I'm going to end up having to do the same thing here. So yes, don't forget that it's the thickness, which is part of the mass. But I got to say it at this step because now I can go on to the next step where I have this r squared of the ring, and then let me do like we did before. How did I get rid? In this case, it was the mass of a little, you know, length here, a little chunk. But here, it's the mass of the ring. And so can't I do it by density again? So if I come over here and say, let's look at that ring, how would I get density? What would density be equal to? Okay, one, which I'm not going to need till later on, but just like around here, I would agree that it's total mass over total area. All right, let me not put that one first, but I am going to need it later. So as long as you set it first, I'll put it over here. So the density would be the total mass, and so should I put m of the whole disk divided by what? Okay, and what's the area? Okay, so this would be, and there brings up a question, what do you want to label for the radius of this? See, because I've been using an R here, but this has been a capital R. I went to a capital R because over here I used a little r. And I'm kind of out of R's. Okay? But your author does this, and I don't know if this is better or not. He just calls it radius of disk and still leaves it as a capital R. So is that better or worse? Yeah, I haven't decided over the years. It's nice to leave it as an R because we are talking about the radius. What's bad is now we're, you know, what radius? In this case, it's the whole radius of the disk, whereas right now in my equation, this R is representing the radius of the ring. So I like to just kind of spell it out. So, but you are right. It's mass of the disk, not to be confused with mass of the ring, and it is radius of the disk, not to be confused with radius of the ring. Now that's the whole big picture, but it was this one in between that I wanted. What about a little bit of mass? Because I'd like to get rid of this, is my point. So this would be a little bit of mass, meaning the little bit of mass of the ring. So not the whole mass of the whole disk, but if you could, you know, section out and cut out a little piece, what's the mass of that little ring? Over what? Yeah, what area? Oh, the area of the ring. How do I get the area of the ring? So it's the part in blue, right? Okay, so how do I get the area of that thing in blue? Okay, I heard some are circumference, so that would be 2 pi r of ring times what? The thickness. And how thick is it? Yeah, that's that limiting thing, dr. Does that make sense? Because again, this is a geometric thing. You got to see this physical picture. And I'll say it again, you know, solving these integral here is really more about, you know, seeing the physics of it. It's far more done here by the physics than it is by some fancy math and, you know, integration by parts. And there's really not anything fancy. I mean, this wasn't a hard integral here, right? I think the hard part was getting here. Same thing here. This wasn't a hard integral. The hard part was knowing what the physics was behind it. And the same thing here. This is not going to be a hard integral, but maybe the hard part is converting it into an integral and noticing that it's the ring that gets smaller. And then once the ring gets smaller, how does that associate then with the thickness? And so this is the thickness that you were asking about earlier, the thickness of that ring. So I could replace this with rho times 2 pi radius of ring integral of dr of the ring. Fair enough? And that's an important step, just like the step back here with the rod, because we converted it then from a dm to a dx, so we can actually then pick the physical limits of our integral. I just did the same thing. It is this important step, converting the dm into a dr, so now I can get the physical limit. So what are we adding up? We're adding up these rings. Where do we start with? So the first ring starts with a radius of 0 and gets bigger until we get to the radius of the whole disk. And now it's going to be a very easy integral. That's not the hard thing. The hard thing is right there, that equation, coming up with it. All right, so now I can pull out the things that are constant. Rho is a constant. 2 pi is a constant. And I have an integral then from 0 to r. And maybe I should put r of the disk. And then this would be the radius of the ring cubed dr of the ring. And so that is just an integral of a polynomial. And I know you know how to do the integral of a polynomial. That would be then r to the 4th over 4, right? And then we would evaluate it from 0 to radius of disk. So when we substitute that in, we get that. And now we can make the final step, which you've already helped me with. Couldn't we get rid of density? And so just like we used density here to go from a dm to a dx, we did the same thing. And now once we have it, we can now get rid of density by looking at the whole mass over the whole area. And so that step here would then be mass of the disk divided by pi divided by r of the disk squared. And so there's density. I've got the 2 pi. Then I've got the r to the 4th power of the disk. And then I've got r to the 4th. So 2 of these downstairs cancel off. The pi's cancel off. And at least that 2 with a partial of the 4 cancel off. And you end up with 1/2 times the mass of the disk times the radius of the disk squared. Ta-da! And so there's the moment of inertia. So we've calculated the moment of inertia of 3 things. That's probably good enough for now. But I think you can see now, as you start doing the problems, aren't the other objects then probably going to be combinations of these? In other words, if I had something that maybe was a propeller, ooh, there's a rod spinning around its center, with maybe a cap piece on it, what's the moment of inertia of my propeller? A rod and a disc, right? And I add them together. And they're both around their center. So take what is it here plus what is it there. And so you just add the two together. And so any of you who've started working on the homework problems will see there's one in particular that's a bit challenging. It's got 3 rods hooked together in a very three-dimensional picture, and it says, all right, what is the moment of inertia of that one? Well, let me not give too much away from it because you'll learn a lot as you struggle through it. So I'll let you think about those 3, but it's a good problem to do. Another one is a car tire. It says, what is the moment of inertia of a car tire? And it describes the tire. And I'll give you kind of a hint here. It says you can think of the car tire as 2 sidewalls with a tread around the outside. Okay, so let's take this disc, but pretend there was a hole cut out in the middle. That would be one of the sidewalls, right? So how would you get the moment of inertia of that object? What would be different here? Yeah, I wouldn't have started at 0, right? I would have started at inner radius to outer radius. But other than that, it would be a sum of a bunch of rings. So all this would still be the same. I would end up with here, and I would say this is inner radius to outer radius. And so I would get, you know, a ring. Maybe this probably isn't too good of an example, except it does have a hole cut out. But I would put inner radius and then put outer radius. And that would be the sidewall. And then double it for the sidewall behind it. And then what am I going to do with the tread? Ooh. Yeah, it's pretty easy. All of it has the same mass, right? It's like a hoop. Yay! All right, so take 2 hollow discs, add them together with 1 hoop, and you got a tire. And so that's the whole idea of finding the moment of inertia of this tire.
Why do you have to do the inner radius minus the outer radius?
Inner radius minus outer radius? I'm not sure I follow that.
The bound, then, start at 0. We just start.
Yeah, right. So you would, the difference would be you would have something that starts at, I'll call it inner radius, and you'd go to outer radius. Because you would add up a ring and go all the way in. And so right here, you know, I would have, in this case, I had 0 to radius of disk. You would have inner radius to outer radius, as you were adding it up. Fair enough? Well, let's add one more thing to this, because chances are pretty good that other things would happen, maybe something like this. Oh, let me kind of take this off and say, all right, maybe here is the rod, and so if I let this go, clearly the rod would be spinning around its center. So that's a pretty easy one. I've already done that. That's 1/12. But what if I also have that? So I have the disc, I have the hoop, I have the rod. They're all rotating. But this is a step up. What's different about this? Yeah, they're not both the disc and the hoop are not rotating around its center, are they? Now the rod is. But how do I add the disc and the hoop? All right, so the last piece of this, before we better move on to other things, is say, okay, what I said a few moments ago. Could you get the moment of inertia of something that is not at its center? And once you have it at its center, it is pretty easy. Your author does a good job of deriving it, and since we're a little tight on time, I thought I would not take the time to derive it, but at least give you the results here. And this is called the parallel axis theorem. It is one of the 3 things you will do in the lab today. I hope you like today's lab. It can be a little long only because you guys are still learning what do we mean by moments of inertia. It's not supposed to be a long lab, but I have noticed in the past that students do kind of struggle with it at times. But here's what today's lab is. Today's lab has an instrument a lot like you're seeing here. Yours is a little more sophisticated because it hooks to the computer and can measure the rotation and all of that. But your first step is to put a disc on here just by itself and find out what is the rotational inertia of a disc. What you hopefully will find is it is what? 1/2 mr squared. So you will calculate this separately, but you will also put it on here and measure its inertia effect. We'll talk about that in lab, how you measure it. But as you measure its inertia effect, hopefully what you calculate in this equation and what you measure on your apparatus agree. And then after you do the disc, you do this one. You do the hoop. You put a hoop on here. And you, again, same thing. You rotate it and experimentally find what is the rotational inertia. And what you do is you can compare it with this equation. You don't do a rod, but the last thing you do is this. It's called the parallel axis theorem. And it says, what if you were to rotate something, and that one I'm trying to show you, that's off-center here. And so what if you have something like this disc here, and instead of rotating it about its center, you now rotate it around some other axis, a distance d from its center. And you could imagine then the integral here would be a little bit different. And like I said, your author does a good job of deriving it. So let me give you the results here. Your author says the moment of inertia here, I, and I should put I, a distance d from center then, called the parallel axis theorem, is start with what is it about its center and add to it really a very simple calculation. And I got to admit, when you start the integral, that's the last thing you thought it was going to simplify to. But it is just take the mass of that object and add that extra distance. Probably when you get the final result doesn't surprise you, because doesn't the moment of inertia have to do with the mass and the distance away? And so when it's all said and done, you're not all that surprised to realize it's the same as about its center plus the extra distance that you added on here. So coming back to this contraption, if this was the homework test or the homework problem or test problem, and it said, what is the moment of inertia of something like this? Well, if I know the mass and radius of this one, mass and radius of this one, and mass and length of the rod, couldn't I get it? And I guess I'd have to know positions. But I would take the rod about its center, 1/12 ml squared. Then I would take the hoop, mr squared. But then in addition to the hoop, I would add in this extra 25 centimeters. And then the same thing here. Here's the disc, 1/2 mr squared, plus the extra 25 centimeters there. Okay? And so then I would just add those 3 objects together. So keep this one in mind. This is a really good one. It allows us then to do some pretty creative shapes, because now we don't have to always be rotating around its center. We can be off of center. And we can have multiple objects. And so that's what you will see in the homework problem, as I pointed out with the well, the tire wasn't a good example of off-center. The tire the sidewalls and the treads all rotate around its center. But the 3 rods is a good one. For those of you who haven't looked at it yet, the 3 rods look like this in a 3-dimensional shape. You take 2 of them at right angles and you take a 3rd one perpendicular to that. So it's a 3-dimensional picture. And it kind of looks like that. And then you connect it right here and you... These things are kind of slippery. And they're too short. Maybe I should make it longer. Maybe you could see it better if I made 3 rods. And so 1, 2, 3. 3-dimensional plus sign. I don't know what to call it. Okay. But yeah, it's an XYZ axis. And then you hold it right here and let it go. Well, I hope you can see this rod. Isn't this just a rod about its end point? And we already know the rod about its center was 1/12. Couldn't we then find out what the rod is by its end point? Yeah, so use the parallel axis theorem to find this one. Okay, so there's one of them. That's probably the easiest of the 3. Okay, so it does this. How about this one here? So here it is. Here's the axis. Doesn't it do this? Well, don't we know it here? And I think this was a little maybe harder to visualize, but the parallel axis theorem doesn't say you have to go along the object. Can't you go here? So you're just off axis. So same thing, use the parallel axis theorem. You know it's 1/12 here. Go that far over. Doesn't matter where you go over, just as long as your new axis is parallel, which is why it's called the parallel axis theorem. So you can rotate it here, or 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 so here. So that's just a parallel axis theorem too. So just like you got this one, parallel axis, you get this one, parallel axis. And then the last one is actually the simplest one of all. How do you do that one? Now this one you got to be a little careful. You can't do a parallel axis because this is the axis we know 1/12, and we're looking at an axis that's not parallel to it. But yeah, isn't all the mass the same distance away? This one's trivial, right? And so you can recalculate it, but it's kind of like doing the hoop. All the mass is the same distance away. And then add the 3 together. So good luck. And like I said, I think this is the one of the harder things of the semester to calculate, which is why we'll keep seeing it for 3 semesters, and which is also why we better move on and go to the second hardest thing, which is now torque. And so what I've shown you so far is, and we got involved in this discussion when we talked about kinetic energy. But coming back to this chart here and maybe clearing the board a little bit, is one other part that we haven't talked about is the equivalent to Newton's 3 laws of motion. And I don't know if I can even put it in the chart because it's just words. What did Newton's first law say?
An object in motion.
Right. So if I take an object here and say, okay, here's an object, and it's in motion. It continues in a motion in a straight line unless acted upon by a force. Oops, this one's a little bit uphill, so maybe it's not going to illustrate it quite as well. But you might remember us rolling this one and saying, look, the object keeps going, keep going, keep going, unless what? Acted upon by a net force. So, how would you describe a spinning object? An object in motion keeps going, keeps spinning unless acted upon by a net torque. And for those of you 102 who might remember, we changed the semantics here, and it's not just semantics. It's going to have another mathematical consequence too that makes it harder to deal with. But for right now, I'll just do the semantics. Don't call this a force. It is a torque. Torques make things start spinning or stop spinning. Okay, so I'm applying a torque. I'm applying a torque. Now, part of the torque, as we'll see, happens to be my hand of force. Okay, but Newton's first law says an object at rest will remain at rest. An object not spinning will remain not spinning. An object already moving or an object already spinning, to make it move, it needs a force. To make it rotate, it needs a torque. Okay, and so the new quantity here is torque. And we like to use the symbol tau. It's the equivalent to F. When we did translational motion, we measured it in newtons. As we now do rotational, we are going to see that it is not only a force, but also what we'll call a lever arm. Let's see if this helps. Let me take this apart here for a moment. Let me wind this back up and then put together the pieces of the puzzle that I have just done for the last day and a half here. Is the first thing I did was talk about, oops, I got my hand stuck in there. Okay. First thing I did was talk about rotational inertia. And so this little apparatus, I think, does a good job of showing you both rotational inertia and torque. Let me just hang a small weight here. This is a small 20 grams. In fact, it's exactly like the apparatus you're about to do here when you go into lab. If I let it go, it starts to unwind. And I would say, in this case, it unwinds pretty quickly. It has a large angular acceleration. What do you think might happen if I were to put this cylinder on top of it? And I would say now, I'm still applying the same torque, but does it unwind as quickly? No. Why not? More what? More rotational inertia, right? And I would say more rotational inertia because I put more mass on here. But now, let me watch one more step. What if I left this on here and moved them out? I think I showed this one, didn't I? Yeah, or they're out here. All right, so if you go out here, then what do you expect to see here? Yeah, so because the mass is further out, the rotational inertia is greater, and so for the same torque, applying it, I get less acceleration. And what I'm trying to show you here, at least at the first part of this, is that I have changed the rotational inertia. Could I also change, say, the torque? And so let me put the weights back together and leave them in the center and ask you this. Watch the second half of this experiment. First of all, just watch it unwind a minute. So you got a good visual picture of it unwinding. Okay, that's the angular acceleration. What if I wind it up so that the string is now on this lower pulley down here in the bottom? What are you noticing different about this pulley down here? Smaller, right? It's the same weight still pulling on it, but it's pulling on it with a smaller, what we're going to call a lever arm. Do I get the same acceleration? No. And so this is trying to illustrate that the torque you get is not just based upon how much weight you hang, which you probably would have guessed if I put this big old weight it would have unwound more, but it's also dependent on what is the lever arm or what is the distance. The illustration I probably used for you in 102, I guess, was that one, but also the door. The door is kind of nice because if you come up to a door and you go to open it, the first question about semantics, as I open the door, would I want to apply a force or a torque to the door? Torque, right? And so now that our problems are getting more complicated, we have to ask, are we looking at the door to translate or are we looking at the door to rotate? And I think obviously in this case we want the door to rotate. It's got a hinge, it's got a pivot, so we are interested in its rotation. We are interested in its angular motion. And so we are interested in a torque applied to the door, not the force applied to the door. And what I'm trying to point out here is torque then is more than just the force. I mean, clearly I could come over here and apply a big force and really open the door, right? So a big force gives it a big torque. But how else could I affect the torque on this door? Yeah, and I say the door is a good one because most likely at one point in your life you probably came up to a door not realizing which side the hinge was on, and if you push on this side, it'll open. But you have to push really hard to get that same amount of torque as if you were to push right here. So why do I have to push so much harder here compared to here? Yeah, and so the idea here is torque is more than force. It is also that lever arm. Let me see if I can draw a picture here. So, getting my green pen here and coming over here and clearing this board here. If I have something I want to rotate, so for the sake of discussion, this will be a bolt. So there's my wrench. And I come along and I grab the wrench, say right there. I think you would see how it would be different where I grab the wrench and also what direction I apply that force. So if I was trying to say loosen this wrench, I want to apply a force or a torque? Torque, right? The correct word here is torque. I want this thing to rotate. Now the rotational axis is probably right there, you know, in the center of all the threads. Okay, so there's the bolt head and there's the rotational axis. And so this distance right here, let me call this R. Now what's the best direction for me to push to get this to turn? Would you push straight towards the bolt? No. How would you push? Wouldn't that kind of make the most sense? You want that thing to push? And so what I'm trying to say here is torque is not just force. Yes, that is part of it. But it is also a lever arm. How far away did you apply that? Which again, like I said, very easily noticed on the door. If you have a long lever arm here and you go to open the door, you end up applying a lot of torque to the door. Not because you have a lot of force, but because you have a lot of distance. That's why the units here, which I already put, but the units here are, what are the units for torque? Newton and a meter. So it's a Newton times a meter. Now warning here, we saw Newton times a meter before. We called it a joule. Don't call this a joule because we're not talking about energy here. And so that's how we'll distinguish. If you want to talk about energy, then use the word joule. But if you want to use torque, don't use joule, right? Leave it alone as a Newton meter. So I will put Newton meter. I won't try to call that a joule because I'm not talking about joule. I'm talking about a torque, okay? And so I'll call torque a Newton meter. I'll call work a joule, okay? So there's my lever arm. Maybe another example before I add a little subtlety here and go past 102, because all of this you saw in 102. But another good example is just the riding of a bicycle. If you've ever ridden a bicycle, you will know there are times where you don't really feel like pushing very hard with the pedals. So how can you get a lot of torque without having a lot of force from your legs? Change the lever arm. And so you have a gear system. On mini bikes would have a multiple gear system, and the idea is to let the chain go around a different size sprocket in the back. And so as you go to apply the torque to that back wheel, it is a combination of the force you are applying and the lever arm. And so you put the bike into a lower gear to get more torque. Usually when you're trying to go up the hill, you say, okay, I'm going to go up the hill, I want more torque. And I don't want to get more torque by standing up and pushing hard. I want to get more torque by a different lever. So you change the gear on it. So both of those illustrate it. Now, let's go one step further. Something we didn't do in Physics 102. What if we were to change this force? So let me kind of get rid of the force here on my wrench and do this. What if I did not apply a force that was perpendicular to the and I don't want to get away from the word lever arm now, but maybe for one last time I'll call that the lever arm, because we're going to modify our definition of lever arm here in just a second. But what happens there? Right, that's why we did all of our components. We could say, look, what this really is this could be thought of as a force that is tangential to the circle and one that is radial to the circle, right? And if you think about the one that is radial, straight in, what does that do to this bolt? Does it turn it at all? No. If it's enough force, you might shear it off and say, okay, I'm going to push on this bolt and snap it off. But it's this part that is trying to make a translational motion. Or if this is a bolt on a car, you end up kind of pushing the car forward if you can, you know. But this has nothing to do with the rotation. So to make this a little bit better here, and to put an angle in here, let's do this. Let's call this angle phi. The angle that is between our R, so how R being the distance from the pivoting axis to where you're applying the force, okay, there's R, and then F being this force. So if this is phi, which means that this would be phi, the part of the force we want is the sine of phi. So this becomes F sine phi R. And so that's what we did not do in 102, because we did not do trig functions and we didn't do components. But now that you're more sophisticated in your math, you know we've been doing that. So I don't think it's a big step. It's not something that I think is too surprising. But it does say this then, that torque is by far more complicated than just force. When you go to calculate or think about a torque, there's three factors you got to think about. Number one, what is the force? Number two, what is the distance away that you are applying that force? But then number three, what's new for this semester is what angle are you applying that force? Because if you were to apply this force straight in, like this, what would phi be? 0. And then what would your torque be? 0. You wouldn't be trying to rotate this thing at all. Exactly. All you're doing is pushing on it. And you would be trying to translate it, right? You would be, if this was part of the car, you would end up pushing the car forward if the brake was off, right? But you would not in any way turn the bolt. And so that would make sense. You are only interested in how much of the force turns the bolt, how much of it is perpendicular. So, adding this in our long list of similarities here, I will put the equation here. Torque then is F sine phi times r. Now I will tell you, if this helps, I think since this is the first time you see it, and because it's the first time you see it, I think every problem here in chapter 10, the angle is 90 degrees. The author says, well, now 90 degrees. It won't stay that way, okay? It will change, okay? And I'm not even sure it changes in chapter 11, maybe once or twice, but a lot in chapter 12. Chapter 12, we have all kinds of crazy angles the force is applying to. So keep in mind that we are talking about the possibility of different angles, even though maybe in this chapter we only deal with 90 degrees. And that's what's really nice about a string wrapped around a pulley. I mean, what do you notice about this string around the pulley? Look how it comes off. What angle does it come off at? Yeah, if you were to draw a little picture here, you would see, okay, here's the big disc, here's the pulley underneath, here's the pivoting axis, here's the string, and here's the R. They always come off at 90 degrees. And so that's why we'll use a string a lot in this chapter. You'll use it in the lab today. Say, hey, we're just going to pull it off at 90 degrees. Yeah.
So what about the bottom pulley on that little doesn't it pull out?
Ah, so it really wouldn't be 90 degrees in that case, would it? So maybe I should restate that. In a two-dimensional picture, it's going to come off tangential, but it could be angled up, and therefore we do have to put in an angle also. Let's wait until chapter 12 before we do that. And even then we'll just touch on it. That's more of next semester for those of you who take statics, engineering, whatever, 115. So good. You guys are asking some good questions, because obviously there is one step at a time. You know, we got to learn this. You learned 102, now you're learning physics 121, and next year you'll do more and more and more. And so each one adds to it, especially when you get into 3 dimensions. Calculating a torque in 3 dimensions is a bit harder. So it's a good thing you know matrices, determinants of matrices, or you're learning them quickly so you can apply the calculation of a torque in 3 dimensions. So short answer is, we'll keep it simple, 2-dimensional, just draw it in the plane. Okay, so there's the idea of torque. Now, why am I bringing all of this up? Well, finally we can get to almost the end of the chapter here with this, is that now that we've done Newton's first law of motion, and we've learned the word torque instead of force, what does Newton's second law say? Acceleration is what? Okay, force. Now really it's net force, right? Over mass. So what do you think Newton's second law is going to be here for rotation?
Alpha, or rotational.
Yeah, alpha, rotational acceleration is equal to what? Yeah, net torque over rotational inertia. Exactly. Yep. And so if you see that, then you're sitting well with the analogies, and you probably have done quite well, because, like I said, this chapter does not seem nearly as long or nearly as hard if you stop and say, how would I have done this problem if it was a translational problem? Now, how do I do it? So when they came to Newton's second law, we said, hey, what I would do is draw a free body diagram. And I would draw the free body diagram and look at all the forces. Add up all the forces and set it equal to MA. So what am I going to do when I have something that rotates? Draw the free body diagram. Add up all the torques. Set it equal to I alpha, and then solve it. So you're going to go through exactly those same 4 steps. It's just calculating torques and calculating I. I must admit, are a bit harder. Yeah. And so we'll do that. Well, that kind of ends the chapter right there. Maybe the best thing I can do is do some more examples for you, even though I know we're tight on time, but this is well worth giving you a chance to think about some of these. So I'll go into chapter 11 here and open up the back and say, all right, now that we've done kinetic energies. We've done Newton's second law. We've done kinematics. I guess we really haven't done any new gravitational potential energy. There wouldn't really be anything new. That's why we didn't mention it. There is one thing we've done that we haven't mentioned. Anybody know what we're missing? No, springs, you're right. We haven't done springs, but there's nothing real new about the springs and rotation of springs. And friction would just be another force, but where that friction is applied would result in a torque. So you're right, we haven't really done it, but I think you're ready to do it, so we'll do those by examples. But anything missing here? Momentum. Right? And I don't know why your author chooses to not talk about momentum. After he's talked about everything else, he waits to talk about momentum in chapter 11. So I too will wait for chapter 11, okay? But he does a good job at the end here of chapter 10 and say, let's look at energy again. Let's do this. Let's take a look at an object rolling down the hill. And so I said open my book, but I guess I spoke too quickly. I want to do one that's not in the back of your book first. I just want to roll something down the hill. Just, here we go. We're at the top of the hill. And for the first time, we're going to have our objects roll. Right? That's how far we've come. We can now calculate a rolling object. All right. So, welcome to 1685. Okay, we're just past Newton here, and we're just getting things to rotate. I say that jokingly, but if this helps, remember this. You now know more than Newton. The most math he knew was calculus. You know that. And he knew Newton's 3 laws of motion. And you know that. And now beyond. So you're smarter than Newton if anybody challenges you. Although it's still 1685. All right. So we got a lot more to learn, obviously, here. But let's, like I said, talk about rolling. So I want to emphasize, because I think if you lose track of this big picture, you get yourself a little confused. Remember, this was the neat thing about chapter 9. And the hard thing about chapter 9, for the first time we gave our object size. We talked about center of mass. And now, as we got into this chapter, once we gave it size, for the first time we can make it roll. So before I actually do it rolling, let's say, what if it didn't roll? Let's just repeat what we had been doing all the way back in chapter, I'm going to use energy, so this would be like a chapter 7. I'd say, okay, look, if this object starts at some height h, and it goes down the ramp, and it finishes down here at the bottom, and just to keep it simple, no friction, what's the speed down at the bottom? Oh, could you calculate it?
Sure. Yeah.
Sure. So you would say, well, initial energy is equal to final energy. And you would start off and say, well, if we start from rest, then it has only potential energy. Right? mg h, if you will. And then, as it goes down the hill, you would say it no longer has h. But it has kinetic energy, 1/2 mv squared. And so one of the simplest calculations would be just to get the speed at the bottom of the hill by saying it's the square root of 2gh. But now let's look at what we've done at the end of chapter 9, which we gave our object size. And now that we've got it rolling also, when you come over to here and you give it size, that alone brings up some issues here. Because when it rolls down the hill, in this simple model where I didn't give my object size, what did I say its height was? Okay, so what do I need to do to deal with a problem that gives our object dimension, gives it size? Yeah, first thing I want to do is find its center of mass. So we're just going to let this thing roll down the hill. I'll call it a symmetric object. Let's not even say if it's a ball or a hoop or a disc. But in a moment, I will do the hoop and the disc both. So let me not specify which one it is, but I will do both of them. But I think you would agree that its center of mass is the center of the object. So when I say it has a height h, what do you mean by height h?
From the center of mass.
Center of mass to center of mass. So maybe to be a little more accurate, let's not call the ground 0, but let's call the center of mass as it gets onto this flat section, let's call that 0. See, and that question hadn't even come up until we got into chapter 9, now that we have size to it. But sounds like you guys are familiar with that. You caught that right away. So when I say starting with a height h here, what I mean is the center of mass of this rolling object is a height h above where the center mass is going to be when it gets down to this level turf. So that's what I mean by h. So I can compare this object, which didn't have any dimensions or size, to this one. This one does have size, and then it also rolls. Yeah.
But you can have static friction.
Okay, so now the next question here is, this thing begins to roll, right? Or does it roll? What is needed to make it roll? So let's come back to this. What if there was no friction? Well, this is how we said this one, right? No friction. What if there was no friction to this one? Yeah, there would be nothing to make it roll. I mean, let's do the free body diagram. What is making this thing roll? Free body diagram. Here is that little wheel or disc or hoop, whatever it is up here. What are the forces on it?
Gravity.
Okay. I would agree that one of them is gravity. Let me stop right there. There is the force of gravity. How much torque do you get from the force of gravity?
So you get 9.
Where gravity's angled at compared to
So in other words, we do have a force, but that doesn't mean we have a torque, does it? Because in this case, what would R be? 0. If we're looking at it rotating about its center, and the force of gravity is at its center, what is the distance from its center to its center? Right? Force of gravity here does not make this thing rotate. So do we have a force of gravity? Yes. And if you were to let it go on its own, like right here, if you took a ball and let it go, what happens? It translates. It has a force, but does it have a torque? No. Does it rotate as it falls? No. Okay? And so again, that's this tough section, I think, of this class, is you got to be thinking about both at the same time. What does that force do? Does that force, if it is a force, it tends to make it translate. Is it also a torque? If it's a torque, it tends to make it rotate. And if all you did was take a ball and hold it up here and let it go, force of gravity would make it translate, but the force of gravity would not make it rotate. So, force of gravity is applying a force, but not a torque. So that's not what makes it rotate here. What other forces would we have in our case? Normal. Okay, the normal force. So the normal force would be right here, and I picked a round object purposely because it may be contact here, and that normal force would of course be touching the ball at its rim, but pointing where? Yeah, right towards its center. So I ask again, we have a force, yes, but how much torque do we get from that force?
The normal force times the contributes to the force of friction.
So I would say, well, there's a force, N. I would even say, how far away is the normal force from the rotational point? Okay, radius. But this is the one that I want you to focus this time. What's the angle? 0. What's the sign of 0? 0. So how much torque do you get from the normal? 0, right? And so a normal force pushing on it doesn't make it rotate either. You're pushing right towards the center. I've erased it now, but it's like that bolt. If this is the bolt and you take the wrench and you push the wrench straight towards the bolt, that doesn't make the bolt rotate at all, does it? Okay? And so you're beginning to see here that the problems get a bit more complicated because it's not just how much force, but it's also how much torque. So you got to look at how much force to see how it is translating. Then you have to also look at how much torque to see how does it rotate. And both of these are forces, yes, but neither one of them makes the ball rotate. What's going to make the ball rotate? We need some friction here. If this is all we had, if this was a frictionless surface, what would happen to this ball? It would go down the hill without rotating, right? It would have a force on it, but it wouldn't have a torque on it. It would be just like this block. This block would go down the hill and be going this speed when it goes down, so it has no rotation with it. But that's why I'm going to say we can't compare these two until we say, not only does this object have size and it rolls, in order to roll it must have friction. So we want to have friction here in this discussion. I didn't want it here. I wanted to keep it simple and say, okay, what did we do and what are now we doing? And so you can compare and contrast, but this one must have the friction. So where is the friction here? And so there would be the friction. And would that give you a torque? Oh yeah. This would be F for friction. What would the distance away be? The radius. What would the angle be? 90 degrees, right? Sine of 90, that's 1. So that is giving me the torque. That is what is making this object roll. Okay. Now, question. Would it be a static friction or a kinetic friction? Yeah, most likely it's static. It could be either one, right? I mean, normally a wheel rolls like this. And see how there's no sliding going on between the rubber tire and the wood? And so what kind of friction is that? Static. So most likely it's static. But could it be doing something like this? Right. So there are times where we get what we call not pure rolling. Okay? But we'll build up to that. We'll just start with the simple case. Pure rolling. All right? So when it comes to pure rolling, I'm going to put a little S in there to say, look, this is the simplest case I can have. I can't have a case of no friction. No friction doesn't allow it to roll. And that's too simple. We're way past that. I wish it was that simple. I remember that chapter 1. Convert 100 centimeters into meters. Man, that was a simple problem. Yeah. Wouldn't it be great if that was a final exam question, you know? We've come a long way from there. And now we've got problems that, you know, to look at them, we can't just look at no friction. We've got to look at some friction. And in this case, let's just look at static friction. Kinetic friction will show up later, sure. But for right now, let's just have what we call pure rolling here. But I have to have friction is my point. The friction is what gives it some rolling here. Without that, I wouldn't have it. But this gives me an opportunity to say, did you see how I kind of solved the problem? I analyzed it. I drew the free body diagram. I looked at the forces involved. I looked at the forces and I looked how those forces were torques. And the forces made the translation and the torques made the rotation. That's what I wanted you to see, right? That little pattern, that little free body diagram. Now, the other part of this is now that we realize we do have friction and we realize it's a static friction, when we go to calculate our energy, let's see what we come up with. Starting on this side of the equation like we had here, I think you would still say, well, it starts with some potential energy, mgh, fair enough? Where does it go? So as it goes down the hill and starts to roll across the surface, what kind of energy do I have now? Okay, good. Somebody said, well, no more potential energy. Good. Do I have kinetic energy? Yeah, but I'll take you one step further. It's not just one type of kinetic energy. Don't you have both? Isn't this wheel both rotating and translating? All right, so that is why I picked this as the first to discuss here, is don't forget that you've got both now. This object is both going to be translating and rotating. We didn't have that here. So we still have this 1/2 mv squared, just now we also have a rotation. Now maybe I should ask, any heat? Because we have friction now, right? So do we have any heat?
Yeah. Well, it's going to depend if whether it's a perfect.
Okay, right, good. I'm glad you saw that here. If we're just doing static friction, there's no sliding going on. There's no work and distance going on, right? I mean, there's no force and distance. The work would be 0. So there's no heat created during static friction. So do we create any heat? No. And so that's an important difference. If there was friction here, would we make any heat? Yeah, of course, but it would have been a kinetic friction. So it's the kinetic friction that has the force and the distance. Static friction doesn't do any work, doesn't create any heat. All it does is give it a little nudge, if you will, to make it rotate. In other words, the work done by the static, if you will, it's not heat, and I shouldn't say the word work, because there is no work, but it shows up to make it rotate. And so again, I'll put no heat here. And so in this case, we put 0 heat because it was frictionless. In this case, we put 0 heat, not because there's no friction, and I think that's a little bit of a surprise. Okay, but it's purely just static friction, and that doesn't produce any heat either. It's what makes it roll. In fact, maybe you could even see it right now. Is this object that is now rolling, even though it came from the same height, going to be the same speed as the one without rolling? It's not, is it? Which one's going to be faster? Yeah, this one's going to be faster. Why would you say this one is faster? What do you notice? Yeah, you have the same energy to start with. But you don't have as much translational kinetic. Here, all of it went to translation. What are you saying here? Some of it went into rotation. And so this rotating object should have a slower speed here because of this. In fact, you can even see it right here in this, what I'll call a race. I'll take this out of the way and say, okay, let's make a little race down the hill. Here is an object that, other than it has wheels, forget the wheels, but the object itself really doesn't rotate, right? It just goes down the hill. The wheels are here because I want to make a frictionless surface, and I can't really make a frictionless surface. So, but as close as I can, this is an object going down a hill without friction. So let's have it race something that is going to rotate. Are they going to be the same speed at the bottom?
Do they weigh so? Or have the same mass?
Yeah, they have the same mass. But maybe I even should ask that. Does it matter if they have the same mass over here, say, in this equation? So an object that has twice the amount of mass, it's irrelevant what its mass is. All objects going down the hill without friction will have the same speed. And I want you to see that is not true now that we introduce rotation. But I haven't got to rotating things completely yet. But I just want to compare a frictionless object down the hill with a rotating object. Neither one creates any heat, but yet, clearly, this one wins, right? Because this one uses some of its energy to rotate. And you could pick any rotating object, but the rotating object is always going to be a little slower. That's my point there. You let it go. And this one, all of its energy is going to kinetic. This one, or this one, has to put some of its energy into rotation. So this one always wins. But what about these guys? Do these go the same speed? Which one's going to go faster? And I will tell you here, they are the same radius. And maybe even surprising, they're the same mass. This is kind of a light wood, and this is a heavy steel. Turns out it really won't matter about their radius or their mass. We'll go through the math in a second, but this part is, are they going to be the same? I just need enough friction that they don't slide.
What isn't that there for? Is that affect what
The answer is no. I'm wondering if I should do the math first, but the answer is no, because would you get more friction? Yes. But would you also have more inertia? Yes. And the two balance each other. And in fact, maybe before I roll it, I'll go through this math here. Your question was more along the line of Newton's second law. I'm going to do it by energy here. Let's keep working this one out. Let's see, I guess I started in black, so I should continue in black here. But as I go to solve this for the speed, let me do this. Let me just write the mgh. Let me write the 1/2 mv squared. Let me write the 1/2 I. Let's talk about the omega then. If this thing is rolling down here without sliding, didn't we learn the relationship between the translational speed and the rotational speed? Do you remember that one? It was a little formula we had that said the translational speed is equal to the radius times the angular speed. I think we did that last Monday. Maybe it was Wednesday, but I think it was when we started this one. So I'm going to take advantage of that by saying this is V divided by R. And of course it's squared. Because when I do that, then I can have a V squared in each equation. And that will allow me to solve for what I'm asking you, which is what is the speed at the bottom of the hill? And obviously the speed is also related to its rotational speed. That's why the rotating one has a little bit less. Maybe I'll do a couple more pieces of math. I'll multiply everything by 2. I'll even divide by m. And so this comes out to be a 2gh. This comes out to be a 1 plus I over mr squared, v squared. And the nice thing about dividing by an m is I'm starting to make it look like this equation, so I can compare and see how, you know, giving it rotation now compares to without giving it a rotation. But if I put in the 2, the g, the h, and then divide it by the 1 plus I over mr squared, take the square root of all of that, I get my v. And so that's what I was after here. So the first example problem is calculating what is the speed of this rolling object at the bottom of the hill. Notice I solved it by energy. Why did I choose to solve it by energy? And not torques? Why? Oh, okay, but distance, right? When we have a problem involving forces, gravity, and distance, use energy. When you have a problem involving forces or torques and time, use acceleration. And so that was the lesson we learned for translational motion. Keep it going here for rotational motion. And that's what I do. I have it at a certain height. Okay? If it was asking me what's the speed after 3 seconds, I would have probably done this by torques and angular acceleration. But instead it was about height. But you're right, what I was trying to do was compare these two. So since I had done this one by energy, I should do this one by energy so I can compare. And now you begin to see it. What does this equation say compared to this equation? Which one is bigger? Well, obviously this one, right? The translation is obviously a bigger number. It's the same as the numerator here, but this one is 1 plus, and now you have a number, an added number. And so when this denominator is greater than 1, you're obviously going to get a little bit smaller. In fact, we could do the two cases. We could say, well, what is the velocity of the ring And what is the velocity then of the disk? And so if I put my value in for the ring, this is the square root of 2gh. What was I for a ring again? mr squared. So this is just mr squared over mr squared. So this becomes 2gh over 2, which just becomes the square root of gh. And obviously that number is less than this number by 41%, because the square root of 2 is 1.41. And so clearly the object that doesn't rotate is going 41% faster than the ring. And if I look at the disk, I can do the same thing. Putting in the disk, I get the 2, the gh, the 1 plus. And what was the moment of inertia of a disk? 1/2 is what we worked out. So it's 1/2 mr squared. And so this becomes the square root of 2gh. And the mr squared cancels off. And so that becomes 3/2. So this becomes the square root of 4/3 gh. Right? And so that number here is obviously bigger than this number. So this is telling me the disk is actually going to go faster than the ring, which is still slower than the object without rotation. Sure. And so we already saw that this one without rotation beats both of them. What we haven't seen is a contest between the ring and the disk. But now that we see the numbers, which of these two is going to win? The disk. And why does the disk win? Yeah, less rotational inertia, right? This one is a good example of how this has less rotational inertia. Here, all the mass is at its rim. It's hard to get this guy to rotate. Here, the mass is spread out. Some of it is towards its middle. And so this one's a little bit easier to rotate. So sure enough, you put them both on the hill, you let them go. When they don't go the same speed, the disk wins. Hoop comes in last. Cart comes in first. Okay? And all of them was solved here by using this new chapter of saying, okay, let's let them rotate and put together our idea of forces and torques. And so that's my first example, and maybe a hard example, but it's not in the book, but it's an important, I think, a good one. Maybe I should do a little bit easier one here for a second. Let's look at, and I got two listed here in the interest of time, two on kinematics. Maybe I'll just do one on kinematics chapter. I'm in the wrong chapter. Let me go to the end of chapter 10 here. But yeah, I'll just do number 4 first here. Number 4, you will hopefully see just exactly like a chapter 2 problem. It's kinematics. It's things about speed and acceleration and time and distance traveled. It says this in number 4. It says a centrifuge in a medical laboratory is rotating with an angular speed of 3,600 revolutions per minute. It is then switched off. It rotates through 50 revolutions before coming to rest. Assuming the acceleration is constant, angular acceleration is constant, what is the angular acceleration of the centrifuge? Okay? Well, hopefully you see right away. Doesn't that sound like a kinematics problem? A certain starting speed, a certain ending speed, going so many revolutions before it comes to a stop. It even says it's a constant angular acceleration. What does that tell you? You can use those constant kinematic equations. And so if we think about those 4 equations real quick, let's see. They give us the initial speed. They say it is switched off. They give us its final speed. They give its distance traveled. They ask for the acceleration. They do not tell us the time. So which one are you thinking? And that's the one that pops into my mind. It is what we call the third kinematic. It's made of the first two. So you could obviously solve the first one and solve for time and then plug it into the second one. And if you want to do that, that's fine, as we talked many times before. But isn't that where the third one came from? So I'm going to jump all the way to the third one and say the third one was created because it was an equation that did not have time in it. And so instead of taking 2 steps to get there, this is the result of those 2 steps. So let me put it in there. I'll start here with this question. What is the final angular speed? 0. Yeah, 0. Says it comes to a stop. What is the initial angular speed? Yeah, and I'll read it again, but they are going to make you do a little bit of unit conversion. This is like the chapter 1 stuff here. It says you started off with it says a centrifuge in a medical laboratory rotates at an angular speed of 3,600 revolutions per minute. So I'll put 3,600 revolutions per minute. And then maybe I'll do my unit conversion over here. How many radians are in a revolution? Yeah, so 1 revolution is 2 pi radians. So I will substitute 2 pi radians for 1 revolution. So there's your math. What does a revolution equal? Do a substitution. And likewise, let's do this in seconds. So what does 1 minute equal? Yeah, 60 seconds. So let me do a substitution here. Yeah, did you say 30 seconds? All right, but I'll put 60 seconds there. And so that needs to be squared. So there's my first part of the problem. What's the initial speed? And then unit conversion into radians per second. Here's the 2. Here's the angular acceleration. That's what I want to solve for. And now it says, well, what distance did it travel? Well, it says it goes through 50 revolutions before coming to rest. So, all right, well, if you want to put 50 revolutions, fine. But what's a revolution? 2 pi radians. So to convert everything into radians in second, which maybe you don't even need to. They don't really say get it in radians per second squared, but I feel like I should, or at least I picked this because part of it was to do a kinematics and part of it was to do a unit conversion here. So just like you were doing in chapter 2. Chapter 2, you were doing your kinematics and then you were doing your unit conversion at the same time here. And so now it's just a matter of calculator work here. So I can come over here and say, all right, this one is 3,600 times 2 times pi divided by 60, which comes out to be about 377. It's squared, and so that number is now I'm just going to put 377 radians per second squared. And then over here would be, what would that be here? 100, 200? So 200 pi times alpha. And you might even say radians. So one of the radians here will cancel with one of the radians there. But that should give me my alpha. So take the 377 squared, move it to this side, divide that by 200, divide that by pi, and I get an acceleration of a negative 226 radians per second each second. And so this thing is slowing down by 226 radians per second each second.
We can put second squared.
And, oh, you can put second squared, sorry. Yeah, probably better. Get rid of the compound fraction. So negative 226 radians per second squared. Yeah. Yeah.
Do you want to convert it back into revolution?
Yeah, you know, I was just debating that. The general rule is in whatever form they give you, go back. Like if they give you temperature in Celsius and you have to convert to Kelvin, fine, convert it to Kelvin to do the problem, but convert it back, you know, into whatever symbols you gave it. So probably should. So how about we convert it back? Minus 226. This is radians per second squared. If I convert this back into revolutions per 2 pi radian, and then also convert, and here's where I was kind of hesitant because I probably should have mixed units. I mean, to get back, it should be revolutions per minute each second. All right, so which is kind of weird, but I'll go ahead and put 60 seconds per minute here. And so as far as the numbers go, I have 226 divided by 2 divided by pi here, and then times 60. And so this comes out to be 2160, and it would be revolutions per minute each second. Or I suppose you could even do seconds squared. Not sure what to call on that one. But RPMs per second is, yeah. And if we divide by 60, it wouldn't be too bad of a number. So.
You could divide by 60 and get rid of 60.
Yeah, and then I'd have minutes squared, right? I'd have revolutions per minute squared. But I have to have 2 units of time. Either both minutes or both seconds or 1 second, 1 minute, yeah. Yeah. So, and then maybe I shouldn't spend too much time there because I think those are hopefully one of the easier ones. They're the kinematics. They're just like the chapter 2. All right. And so I'll say it again, as I said many times. If you see the analogy, hopefully it you know, works out well for you, because without seeing the analogy, these problems can seem long and very involved here. And in fact, no, I think we've still got a little bit of time, but there's an important one I want to do before we go into lab. So maybe we'll have enough time to get to it. It's number 49. But let's do 35 first. And so just kind of going through the order, we first talked about kinematics. Then we talked about the relationship between linear motion and rotational motion, and that's what this one is. So I'll read 35 here. It says a model airplane has a mass of 0.75 kilograms and is tethered by a wire so that it flies in a circle of 30-meter radius. The airplane engine provides a thrust of 0.8 newtons perpendicular to the tethered wire. A, find the torque that this net thrust produced about the circle. So taking an aerial view, this might be the center of it. You might remember we had a problem like this before where we had the airplane going in a circle, although in that one we kind of angled up and that was important. This one is not really mentioning an angle up, so we'll just say it straight out. But the point is, I'm at the center of the circle now, and that this airplane is out here somewhere. And they say net thrust because there probably is a combination of the thrust from the propeller and the air resistance. And you know how hard those problems were with air resistance. So we're just going to avoid it right now because we've got enough hard problems here with our torque and moment of inertia here. But what he's saying here is there is then a net force of 0.8 newtons. The wire is 30 meters away. The thrust is perpendicular to the wire. And then the question is, what is the torque? So I'll read it again. The model airplane is 0.75 kilograms. It is tethered by a wire, so it flies in a circle of 30 meters in radius. The airplane is tethered to the wire. A, find the torque that this net thrust produces about the center of the circle. So how do I get torque? And I need 3 of them. Oh, 30 meters. Thank you. That's 30 newtons. 30 meters is the distance. And they're perpendicular to each other. But I picked this because it was a good opportunity to list all 3 again, right? So what's the net force? 0.8 newtons. What's the angle? 90 degrees. What's the distance? 30 meters. And so when we put all this together, 8 times 3 is 24 Newton meters, right? And so sine of 90 degrees is 1. So there is the answer to the first one. What is the torque? Okay. And again, notice I did all three. I did the force, I did the distance, but I also did sine of the angle. And like I said, I think every problem in this chapter, I'm quite sure if I remember right, is always 90 degrees. Soon change, but good place to start. All right. B then says, find the angular acceleration of the airplane. Well, how am I going to get angular acceleration? And I suppose I could find linear acceleration and translate it, but I don't think the author wants that because he does make you do torque. So why don't we use Newton's second law, right? All right, so let's find the angular acceleration. So angular acceleration would be the torque divided by the rotational inertia. Now we just did the torque, that was the whole point of A. So this is 24 newtons per meter, or excuse me, Newton meters. I comes, oh, what is I?
Summation of the mass.
Well, I suppose you could say it's a summation of the mass, and technically it is, but again, here's where you got to be a little bit paying close attention to the physical picture here. You have to add up the mass of this airplane. How big is this airplane? Well, it doesn't really say, but I don't know, would you think it's this big? Bigger? Smaller? Probably smaller than this. Maybe at most this. So in other words, how does the size of this airplane compare to 30 meters? All right, so what could you roughly say about all the chunks of mass that make up the airplane? They're roughly 30 meters, aren't they?
Yeah, 3 meters.
Fair enough? In other words, can we treat this really as a point? So no, this is not like the hard ones we just got done showing you with get the rod and get the disc. This is the easier one we saw last week. Just add up the individual points. We don't even have 2 points. We just have 1. So this is really, I'll just take the distance, 30 meters, and square it and say this is the sum of all the little pieces of mass that make it up. And if you add up all the little pieces of mass, what are you going to get? That's the 0.75 kilograms of the airplane itself. So this hopefully illustrates a real tough point here of you need to do this physically, right? You need to stop back and kind of think about what it means. What do these individual pieces mean? And it's not a perfect calculation, if you will. We're not trying to do a perfect mathematical calculation. We're trying to say, you know, what roughly is all of this? And that's this tough, really, question here is where is the pieces of this airplane? And this airplane, let me come back and read it. Did they say how big? They just said a model airplane of mass 0.75 kilograms. So although they don't directly say it, they tell me A, it's a model airplane. B, they give me this small amount of mass. I'm thinking this thing can't be any bigger than this. So one chunk of mass is 29.9 meters. The other chunk is 30.9. I mean, they're all really close to 30. Fair enough? And that's the key here. Okay, stop back and read the math a little bit. Read the question, read into it, kind of interpret it. Okay, what does this really mean? And you're not going to really add up the propeller and the left wing and the right wing and the tail and the cockpit and the fuselage. Why add those together? Aren't they all about 30 meters? So just take out the 30 meters. Then this is the sum of the mass. The sum of the mass is the total mass of the airplane. End of story. That's how you find I. Okay?
Wait, so what's the distance and the radius to that point?
Yeah, so what does R mean in this equation? It's a distance, right? From what? Distance means from what to what? Center of rotation to the chunk of mass. Where's the center of rotation? There. Where's the actual chunk of mass? Way out here. 30, roughly. Maybe a little less, maybe a little more for some pieces. But with a small variation, they're all 30. And I got to admit, that's what's hard to see about this one. You have to understand and be reading the math there. And now once you have that, then we can put that into here. This becomes 30 meters squared. This becomes 0.75 kilograms. And now I can get my calculator and check my units. But my calculator would give me the 24 divided by 30 squared divided by 0.75. And that comes out to be 0.0355 repeating. I should check my units here. Let's see, this says Newton meters. Let me just write out a Newton for starters. There's a Newton spread out. This then would be meters squared. This would be kilograms. So kilogram would cancel with kilograms. Meters squared would cancel with meters squared. And so I'm just left with per second squared, but couldn't I just call that radians per second squared? Since radian is not a real unit, we just throw it in, take it out, whatever we feel like to make it sound nice, right? Which was our argument when we started this. So there it is. My acceleration is 0.0355 radians per second squared.
Do you want to convert that to revolutions or no?
Since they did not put it in revolutions, I wouldn't be tempted to do that. I only did that here because they originally gave me things in revolutions. I converted it to radians, so I probably should go back to revolutions. But whether it be this one or this one on a test, I would be happy with the right answer in whatever units. I mean, unless the problem specifically said, put it in these units. You know, I personally am good with whatever units. It's because you made it clear. This is the answer in these units. Put in different units, going to have a different number. That's fine. But as long as you put the appropriate number with the appropriate units, I don't think there's any reason I or anybody else should take off points for that. You put it in that unit. Like I said, unless the question actually said a particular unit. Well, in the short time we have left here, let's do number 49. 49 is just like the one you're about to do in lab in a few minutes, or some of you in a few minutes, the rest of you in 3 hours. But what you're going to do is you are going to use a rotating platform, and number 49 has a picture that looks just like this. And what they do is they put an object on here. Now in my case, I'll just put this object. When you guys go into lab, you'll have objects that look like this. In this picture, they make it more realistic. This is a picture of what NASA does with their satellites, and Lockheed and others. They put their satellites on there and rotate their satellites to find out what is the rotational inertia of this satellite. So they do a little experiment to find out what is its rotational inertia here. And so let me read the problem. It says, number 49, this problem describes one experimental method for determining the moment of inertia of a well, they say an irregularly shaped object. And I guess what they mean by that is really it could be any object. If it's regular shape, it's easy to calculate, so why do the experiment? But if it has weird shapes and sizes to it, you may not be able to do the calculation very easily, so you would rather measure it and see what it is than calculate it and see what it is. In our lab today, we will do both. we will measure it and then calculate it and see if they don't agree with each other here. Okay? Well, it says here an irregularly shaped object such as the payload for a satellite. Figure 9 shows a counterweight of mass m suspended by a cord wound around a spool of radius little r. So here is the mass that they talk about. I'll call this little m, that they are hanging. And so they hang little mass m where the cord comes up and goes around a spool of radius little r. Now notice they said little m and little r because this object down top has mass, and I don't want you to confuse these two masses. So let's call this capital M and let's call this little m. But this object on top also has a radius, so let's call this capital R, not to be confused with the spool. Okay, little r. All right, well, I'll keep going. Figure 49 shows a counterweight of mass little m suspended by a cord wrapped around a spool of radius little r, forming part of the turntable supporting the object. The turntable can rotate without friction. When the counterweight is released from rest, it descends down a distance h. It acquires a speed v. Show that the moment of inertia is given by this equation. And they have a very long equation here, and I'll write it down here in a second. But let's kind of go through this here. All right, so here is kind of this platform. It's got this spool, something like that. The cord comes off, goes around this pulley, and this is little m, not to be confused with capital M. Fair enough? This then becomes the rotational axis, little r, not to be confused with capital R, which is the radius of the object on top. So let's do a free body diagram for this rotating object. And so if I draw over here free body diagram, and I say, all right, and let's take an aerial view of it. So let's look straight down on it now. So here's the platform. Here's this object on top, which has radius r and mass m. But underneath it is this cord that is tied to it with a radius of a little r, and then it hangs over the pulley of mass m. I'm going to add one more variable. There's a T tension in that cord. So when I look at the rotating object, let's look at this thing that's making it rotate. I think you can see it, I'm hoping anyways. What is making it rotate? Torque. Torque from the tension, which is coming from that little mass. Fair enough? So my first free body diagram and my first equation from my free body diagram would be to say that the torque is equal to I alpha. And the torque then would be what? T from the tension in the string, fair enough? Sine of 90 degrees times the distance away. And so I think the hardest part of this problem is right there, calculating the torque. How do I get the torque for this contraption? And the torque is the tension in the string times that lever arm. Now, maybe I should ask this. This actually takes us back to chapter 5. Is the tension in the string the same as the weight hanging on the end? So more on that in a minute. But it's so tempting to put mg here. Don't. Okay? I said it many times. Does the torque equal mg? No. Does the normal force equal mg? No. Sometimes, yes. So you write it out. In this case, it's no. It doesn't. So don't put tension equals mg. More on that in just a second here. But there would be the torque. There's my I, and there's my alpha. And I'll do nothing more with that quite yet. Let's do another free body diagram. And in a few minutes we can wrap this up. Let me go ahead and do the free body diagram of that little weight m going down. And so I will do another free body diagram. Now this free body diagram is translational motion. And so this is not new in any way. Maybe it's been a while since you've done it. As I said before, I like this chapter. It gives us a chance to review all the stuff we've done before, and hopefully that helps it sink in here. But just to keep my sign convention the same, I kind of figured that as this thing was unwinding, that I was going to call it positive. And I probably should have said that, because traditionally we call a clockwise rotation negative. And do you want me to call it negative? Or is it okay if I call it positive? Yeah, I like to call it positive. I know it's the opposite of our traditional way. But to be consistent, then this goes down. I want to call this positive, which is again opposite of our traditional way. But let's just to keep things positive, I would add it up this way. I would say mg minus t equals to ma. So wouldn't that be the free body diagram and the equation I get from that one? And I've done all that to solve this for t. T then becomes an mg minus an ma. And so this is what I was asking a moment ago. Does the tension equal mg? No. It's mg minus ma. Now I must admit, for the examples I was giving you, I like to keep a pretty small so you can see it. And if a is pretty small, then the tension's pretty close to mg, and so it's really mathematically not that different. You'll see that in the lab. Our accelerations will be pretty small too. So the tension really is very close to mg, unless there's a lot of acceleration. And in our case, there wasn't today in class, and there isn't in the lab. But I'm going to replace this with mg minus ma times r is equal to I alpha. Which means then, if I divide both sides by alpha, don't I have an equation for I? I have an alpha, I have an mg minus, one more step here. Isn't this A, the acceleration over there? Shouldn't that be related to this A, which is the acceleration of this unwinding disk? So sure enough, as this goes down, if it has an acceleration of A, it gets it from the string, which gets it from the acceleration at the point here. How do we get the acceleration of those points if we know the angular acceleration? Well, isn't that what we learned between the rotational and translational parameters? So I can replace A with alpha r. And so this comes down to an mr alpha g minus alpha r is the way I think it is written in your lab manual. Because as we go into lab, as I said, your job is going to be find the moment of inertia of different objects we place up there. You will need to measure then m, r, and alpha. And once you measure those, you can put in your calculator and get there. Now, the problem itself, I'll stop here. The problem itself gives it in a little different form. They don't want angular acceleration. They want height and blah, blah, blah. So we could use conservation of energy and keep working on this. But this is really what I wanted to show you as we go into the lab, because this is how we'll do it in the lab. All right. So, good. More on this.